The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today we're going to talk about the concept of independence. In probability, we say that an event A is independent of an event B if one of two conditions holds. First, if the probability of A given B is just the same as the probability of A, or if B can't happen, namely the probability of B is 0. In other words, A is independent of B if knowing that B happened doesn't change the probability that A is going to happen. So knowing this outcome knowing if this event occurs doesn't influence the probability that A occurs. And there's a special case where they're independent because you know that B can't happen. If the probability of B happening is 0, then everything is independent of B. Now, the typical example that gets used is when you flip two coins. So say we flip two fair independent coins. And let's let B be the event that the first coin is heads. And that means that the probability of B happening is a half, because we've assumed it's a fair coin. And we'll let A be the event that the second coin comes out heads. So we know the probability of A is 1/2, because it's fair. And because they're independent, we can conclude that the probability of A given B is a half, which is the probability of A. In other words, seeing the result of the second coin doesn't tell you anything about the result of the first coin. Now, actually, when you flip two coins, it's not just always the case that they're independent. Can anybody think of an example where you can flip a pair of coins and they're dependent somehow? They're not independent? Yeah?
Well, if you have to get two heads and two tails.
If you have to get two heads or two tails. Well, how might you have to get?
The probability of getting two heads is needs to be 1/4. It's 1/2.
Well, but then they'd be independent in that case. Yeah?
If you glue the coins together.
Yeah. I mean, this is a silly example, but I got two fair coins here. You know, I could clip them together, and now I flip them, and odds are pretty good they're both going to be heads or both be tails. If you know what happened to the right coin, it'll tell you what happened to the left coin. Now, that's a pretty contrived example, but it is illustrative of what happens in practice. In practice, we assume independence, even though there can be subtle dependencies, and this can lead to trouble. In fact, we're going to give a lot of examples where it leads to trouble today and also for the rest of the course, because we're always going to want to assume independence, and when we do, we're going to get very nice results. But things aren't always independent in practice, and establishing independence is a hard thing to do. You know, for that matter, while we're on the subject, we always talk about fair coins. You flip a coin and it's fair. You know, that's not always true either. There's actually a famous mathematician named Percy Diaconis, who used to be down the street at Harvard. And he came and gave a talk one day at MIT in the math department, and he's a probabilist. He does probability theory and is a very cool guy. And so he flipped a coin, got a quarter from someone in the audience, and flipped it. And he flipped it, I think, 10 or 20 straight times, all the way to the roof, caught it, turned it over. Every time it was heads. And he goes, now what's the probability of that happening? Well, it's 1/2 to the 20th or whatever, not very likely. How could he always make it come out heads? Well, Percy was an unusual guy, and in fact, he'd spent months in the strobe lab over at Harvard practicing to make it always rotate 7 times. All right, 3 of them the way up, 1 on the top, and then 3 on the down. He could actually see how many rotations it had done to make sure it was 7, so it always came out heads. Now, he is an unusual fellow. He was one of 10 people in the world that could do a perfect shuffle reliably on a deck of cards. And that's a very hard thing to do. He said he had to practice 8 hours a day for over 6 months to be able to do it every time. In fact, he gave another talk at MIT where he came in and he made magic tricks, actually based on mathematics. And you would cut a deck. He would feel it like this and tell you where you cut it, how many cards were in the part you picked up. And then do his 8 perfect shuffles, which is enough to return a normal 52-card deck back to its original order. And then using this, he could play the game where pick any card, you stick it in, he feels where the card went, and then using mathematics, he could shuffle the deck 8 times and make the card come out anywhere he wanted in the deck. So he had a lot going on upstairs, too. He had an interesting life history. He ran away from home as a young child and joined the traveling circus. And then somehow from there, he joined the faculty at Harvard. There's an amazing story. And actually, another story about Percy is he was the first guy to get kicked out of casinos for card counting. He figured that out way before the MIT team in the movie 21. Down in Puerto Rico, he used to play, and then they finally figured him out, and he got booted. Okay, so back to independence. Let's do another picture example. Say that my sample space looks like this, and I've got 2 events, A and B, and they look like this, so they're disjoint. Are A and B independent? No. In fact, what is the probability of A given B as I've drawn it? 0. Because if B occurs, you're outside of A. And so this does not equal the probability of A as long as it's not 0. So disjoint events don't imply that they're independent. Okay. Now, what's the picture look like for them to be independent? What's the right picture to draw here? So I got my sample space. And say I make this half the sample space be A. Well, then B, to be independent, would look something, I didn't quite draw it. I have to have it be 50-50. Okay, so that if A is 50% of S, like this half, then for A to be independent of B, A intersect B, this part, has to be 50% of B. Because the probability of A given B must equal the probability of A to be independent. So this would be a picture where they are independent. Now, independent events are really nice to work with, and there's in part because they have a very simple rule for computing the probability of an intersection of events. And it's called the product rule for independent events. And that says that if A is independent of B, then the probability of A and B, or A intersect B, is just the product of their probabilities separately. Probability of A times the probability of B. So let's prove this. And there's two cases, depending on whether or not B can happen, if the probability of B is 0 or not. So case 1 is B can't happen. Probability of B is 0. In this case, what's the probability of A and B? B can't happen. 0. If B can't happen, then they both can't. You can't have both of them happening. And that equals the probability of A times the probability of B, because the probability of B is 0. So that case works. And case 2 is the probability of B is bigger than 0. All right, in that case, we have the probability of A and B, A intersect B, well, from the definition is the probability of B times the probability of A given B. We did that last time. And by independence, this is just the probability of A, because A is independent of B. So we're done. All right, in fact, many texts will define independence by this product rule. Many texts will say that A and B are independent if this is true. And it's equivalent, it turns out. We won't prove that here, but if you use this as the definition, then you could derive our definition as a result. So this is an equivalent definition of independence. Another nice fact about independent events is that it's a symmetric relationship. It's called the symmetry of independence. And that says that if A is independent of B, then the reverse is true. B is independent of A. Now, we won't prove that. It's actually easy to see that it's true if this were the definition of independence, because A intersect B is the same as B intersect A. And multiplication is commutative. So it's easy to see it if we use that definition. All right, so because of this, we often just say A and B are independent, because it doesn't matter which order you're taking them in. All right, any questions about the definition so far? All right, let's do some examples. Let's say I have two independent fair coins. And I'm going to have the event A be the situation when the coins match, both heads, both tails. And B is going to be the event that the first coin is heads. And I want to know, are A and B independent? Are those independent events? Well, what's the first answer to this? I mean, A is the event the coins match. B tells me what the first coin was. So the first inclination here is that these are dependent events, right? Because I know something about the first coin, so that might tell me something about the probability they match. Right? There could be some dependence here. Now, in fact, as it's set up, they're independent. And we can check that by just doing the calculation, computing the probability of A given B. Maybe I can do that. I'll do that here. Probability of A given B is, well, the condition that they're going to match, given that the first coin is heads, means it's the same as the second coin being heads. This is the probability the second coin is heads. And that's just 1/2, because it's a fair coin and independent of the first one. Now, the probability of A by itself, the events the coins match, what's that? How much is that? What's the probability the coins match? Quarter plus a quarter. I got a quarter chance of heads, heads, a quarter chance of tails, tails, so it's 1/2. So it works out. Probability of A given B equals the probability of A. They're both 1/2. So these are, A and B are independent events, because that's just the definition. Even though it looked like there might have been some dependence lurking around here. Now, this example that I just did is a little misleading. The intuition they probably are dependent actually is good intuition in this case, because if I don't have fair coins, they are dependent. All right, so in particular, let's look at what happens if the probability of a heads is P and the probability of tails is 1 minus P for both coins. All right, so let's compute probability of A given B. What is it in this case? Well, it's the probability the second coin is heads. What's that? P. All right, because both of them are heads with probability P. They're independent still. The two coins are independent. And now let's look at the probability that the coins match. Well, it's the probability of heads, heads, and probability of tails, tails. Heads, heads is P times P. Tails, tails is 1 minus P squared. Okay, so to be independent, I need this to equal that, or to have probability of B be 0. So A and B are independent if and only if, well, the first case is probability B is 0, which means that P equals 0. Or that has to equal this. So P would have to equal 1 minus 2P plus 2P squared. Just squared that out there. All right, so let's solve this. That happens if and only if 0 equals 1 minus 3P plus 2P squared. That's true if and only if 0 equals, if I factor this, it's 1 minus 2P times 1 minus P. And that's if and only if P is 1/2 or P is 1, the two roots. So if the coins are always heads, they're independent. If they're always tails, the events are independent. Or if they're fair coins, these two events are independent. But anything else, they're not independent anymore. Any questions? And now you can sort of see if the coins are likely to be tails and the first one comes up heads, that should influence the probability the coins match. Should change. Any questions? All right, so there's a nice application of this to getting an edge in ultimate Frisbee. Now, when you're playing ultimate, you got to decide who gets the Frisbee first. And sometimes you don't have a coin to flip, call heads or tails, but you do have the Frisbee. Now, you could flip the Frisbee and call right side up or not, but the problem is the Frisbee is known not to be a fair coin. That when you toss it up in the air, it's likely to wind up on, I guess, the curved edge down. So that wouldn't be fair to call heads or tails. So the standard solution is to flip the two frisbees at the same time, or one frisbee twice, and somebody calls same or different. Okay, that the two frisbees both come up on the same way, or they come up different ways. And then if you called it right, you get to start with a frisbee. And the idea behind this is that simulates a fair coin. That the probability that they're the same is 50-50. What do you think? Is that a fair way to decide who starts first? Yeah. No. Yeah, that's right. It's not. Okay. Now, it is in the case when the coin was fair. But we know the frisbee is not fair. And in fact, you can see this from this probability. This is the probability of a match, okay, which is fine at p equal a half. But in fact, if you analyze this equation, you find out its minimum value is at p equals a half. And as p starts moving away from a half towards 0 or to 1, it gets bigger. And we know that for frisbees, p is not a half. This means that the probability of a match is better than 50%. So if you're ever playing ultimate, always call same, right? Because you're going to have a better than 50-50 chance of getting to start with a frisbee. It's not a fair example. Okay, there's another example of how to make a fair coin from an unbiased coin, from a biased coin to an unbiased coin in homework. Ways of doing this that are fair. Because often you have biased random numbers and you want to get unbiased, or maybe you got a fair coin and you want to make something that comes up heads with probability a third. How do you actually do that in a way that works? Any questions on that? Okay. The next example is from the first O.J. Simpson trial. How many people here know who O.J. Simpson is? Okay, so he's still pretty famous. Now, as you probably know, then he was a famous football player. Back when I was a kid, he was, famous college player. Then he was a famous pro player, and then he was an actor, famous actor. And then he was accused of murdering his wife in a gory knifing, and a friend of his wife's. And ultimately, the jury found him not guilty, but pretty much everybody in the country thought he did it. He looked really guilty. And it was a big media event, one of the first big trial events on TV. And so all the proceedings were on TV, and everybody watched them. We'd all go home to watch the O.J. hearing. It was amazing. Now, during the indictment proceedings, there was a huge dispute over what independence was. And does it matter? The issue arose when the prosecution witness claimed that only 1 in 200 Americans had a certain blood type that matched the blood type found at the scene of the crime, which was alleged to be O.J.'s blood. And this was during the indictment, and back then DNA tests took a long time, and they weren't ready yet. And the witness presented the following facts, and this was the crime lab guy, the police guy. He said that 1 in 10 people, roughly, match type O blood. And that 1 in 5 people match the Rh factor positive. And that 1 in 4 people match a certain kind of marker, which I don't remember what it was. We'll just call it marker XYZ, some other factor of the blood. And then his conclusion was that this means that 1 in 200 match all 3. Factors. And, this seems reasonable because, there's a tenth of the people that have O. If a fifth of them have positive Rh factor, and then a quarter of all of those have this marker, well, that's 1 in 200. Okay? Now, it was important because OJ's blood and the blood at the crime scene both matched all three. So the implication, of course, is that OJ's looking like the guy who did it. And the question was, well, is the 1 in 200 really true? You know, we can sample these three in the populations and see they're true, but is 1 in 200 really true? Now, it would be if, in fact, we'd verified that a fifth of the type O people have positive and a quarter of the O positive people have the XYZ marker. But, well, we don't necessarily know that unless we go figure that out. Okay? If you assume they're independent, then it would be true. The product rule will tell us that if you assume they're independent. So during the trial, a special math defense counsel showed up. Not part of the normal defense team, but he was brought in, you know, as a mathematician and lawyer. And he, you know, crosses the police guy on the stand. And he asked the police guy, the lab guy, if it is known that these three factors are independent. Well, the poor police lab guy had never heard the word independent before, didn't know what it meant, and the defense counsel proceeded to crucify him on the stand. And in the end, all he could say is, look, we just get these things and we multiply them. That's what we're supposed to do. You know, it was a little scary. The actual transcript is, you can still get it. It's a little scary. The same problem arises today with DNA testing. Only there, you got lots of these things. And you multiply them all together, and you get probabilities like 1 in many billion probability of a match. Now, there's probably a higher level of science going on with DNA testing, but it's even harder to really establish independence. You know, if you assume it, fine. The math works out great. You just multiply them together. But how do you know it's really true? How do you know that maybe a lot of the people that have those 4 markers in DNA don't happen to just have the 5th also? That it really is totally unrelated. And to know that for sure, you've got to test hundreds of millions of people, which we really haven't done yet. And not just a few hundred guys in Detroit, to be able to conclude, you know, independence of 1 in a billion probabilities. So for us, this is a lot easier. In the classroom, we assume independence, and we'll keep doing that left and right. But it doesn't mean it's true in reality. In fact, in the last week of class, we'll talk about how a false assumption of independence on mortgage failures led to the subprime mortgage disaster and the recession. And it's all because of some mathematics mistakes that people made. Okay, now this example raises the question of what does independence mean when you have more than 2 events? You know, we defined independence when there's 2 events, but here there's 3. And so to be careful, we got to actually define dependence among more than 2 events. And in this case, we talk about the events as being mutually independent. So let me define that. So if I've got events A1, A2, up to AN, we say they are mutually independent if, and this is a little complicated notation, but for all I and for all sets J that are subsets of the events, but not including I, then the probability that the ith event occurs, given that all the events in the subset occurred, is the same as the probability of the ith event occurring by itself. Or there's a special case where the chance these other events occur is 0. Okay? In other words, a collection of events is mutually independent if any knowledge about any of the rest of the events happening or not, does not influence the event you're looking at for each of those events. So no information about any of the other markers in the blood influences the ith marker for any I. The probabilities are unchanged. Now there's an equivalent definition based on the product rule. Let me show you that version, because that's easier to work with usually. All right, and this is the product rule form. And it says that A1, A2, up to AN are mutually independent if for any subset of the events the probability of each of those events in the subset happening, all of them happening, is simply the product of their individual probabilities. Okay? So independence means that you just, if you want to know the probability of a bunch of events occurring, just multiply them out individually. And that follows from independence, or it could be the definition of independence, depending how you want to do it. So either of these is good enough for you to use as a definition or a result for independence. And so the blood guy, of course, is just multiplying them out because they're assumed to be independent. So it's OK that way. All right, let's do an example. So for example, say we have 3 events. A1, A2, and A3 are mutually independent if these are the things you have to check. Probability A1 and A2 is just the product of A1, probability of A1 times probability of A2. Then you'd check that probability of A1 and A3 is the product of their probabilities. Oops, A1 and A3. And you'd check the probability of A2 and A3 is the product of their probabilities. And there's one more thing to check. What's that? All of them. Yeah, the probability of all of them is the product of each of them together here. So if you want to show that 3 events are mutually independent, these are the 4 things you'd check. That's one way to do it. All right, which is the case in the blood typing in this situation. All right, let's do an example. Well, for example, if I flip 3 unbiased, mutually independent coins, probability of 2 of them being heads is 1/4. The probability of 3 being heads is 1/8, and so forth. Let's do a trickier example. This is a question that was on the final exam a few years ago. And a lot of the class missed it. So now we'll do it here. Say I flip 3 fair, mutually independent coins. And my events are going to be A1 is the event coin 1 matches coin 2. The second event, A2, is the event that coin 2 matches coin 3. And the third event, A3, is the event that coin 3 matches coin 1. And the question was, are these three events mutually independent? All right, prove your answer. All right, so let's try to figure that out. The coins, of course, are mutually independent, but what about these events? So let's start doing it. What's the probability of one of the events occurring? Well, you got to get the two coins at hand to match, so that's the probability of a heads-heads plus probability of a tails-tails. That's a quarter plus a quarter equals a half. Okay. Now the probability of AI and AJ, when I and J are 1 to 3, but different. Well, what is a way of characterizing that case? That, say, event 1 occurred and event 2 occurred. How would I characterize that? Yeah? All of them. Yeah, all the coins are the same. Because if A1 and A2 occur, I know 1 matches 2 and 2 matches 3. If A1 and A3 happen, 1 matches 2 and 1 matches 3, so they're all the same. And the same for A2 and A3. If 2 matches 3 and 3 matches 1, they're all the same. So this is the same as saying all three coins are the same. They could all be heads or all be tails. And that's an eighth plus an eighth, which is a quarter. And that means it equals probability of AI times the probability of AJ, which is what I need for independence. And then they said they're done. They are independent, the three events. You like that answer? What's missing? The last case. They didn't check the last case. And we got to do that to have mutual independence. So let's look at that. The last case is probability A1 intersect A2 intersect A3. What is the probability that all three events occur? Well, the coins all have to match, right? For those, if all the coins match, all three events occur, right? And what's the probability all three coins match? A quarter. It's just the same as this, is a quarter. Does that equal probability of A1 times the probability of A2 times the probability of A3? What's that? An eighth. This is an eighth. They are not equal. They are not mutually independent events. All right? Any questions about that? It might well be something like this in the final this year. A decent chance. So you start going along, looks like they're independent, but you forget to check that last case, which shows they're not mutually independent. So you got to check for all pairs and all subsets of events for mutual independence. Any questions about that? Okay, now this is actually an interesting example because in this case, all pairs were independent. And when that happens, we give that a special name. And it's called pairwise independence. Not too surprising. And that can be useful because there's many times where you do get pairwise independence but not mutual independence. So let me give you that definition. So a collection of events, A1 through AN, are said to be pairwise independent if for all I and j, where I doesn't equal j, ai and aj are independent. All right, now as we saw in this example, it was pairwise independence because the probability of ai and aj equaled the probability of ai times the probability of aj. For any pair, it was true. But it doesn't imply mutual independence. So pairwise does not imply mutual. Mutual would imply pairwise because it's true for every subset of events. All right, so let's go back for OJ and see what would have happened. What can you say about the probability of a blood match for a random person if you only knew that these factors were pairwise independent? Say you only knew that. You didn't know they're mutually independent, but you knew they were pairwise independent in the population. What's the probability that a random person matches? What's the best you can say about the probability a random person matches that blood profile? An upper bound on the probability. Yeah? 1 in 50. Yeah. So what you can say is 1 in 50, but nothing better. So let's see why 1 in 50 works. All right, so let's let M1 be the event you match here, M2 be the event you match there, and M3 be the event you match that. The probability you match all three is upper bounded by the probability you match the first two, because matching all three is a subset of this. Pairwise independence means that this is true. This equals probability of matching the first times probability of matching the second. Probability of matching the first is a 10th. Probability of matching the second is a 5th. So this is 1/50th. And you picked the best two, right? You could have picked these two and said it was at most 1/20th, or those two and said it's at most 1/40th. But you were clever and said, OK, I'm going to take these two and use that as my upper bound, which is 1/50th. And it might well be that 1 in 50 people match all three. That could well be. Because maybe whenever you're O positive, you have marker XYZ. That's possible, potentially. You know, we don't unless we find out otherwise. All right? What if I tell you you can't assume any independence at all? What can you say about the probability of a blood match here for a random person? Yeah? What is it? 1/10. Because if they match all three, they match this, and that probability is 1/10. So it's at most 1/10. And it could be that everybody who's O is O positive and has XYZ. So unless you have more information, that's the best you can say. It might well be that's the answer. Any questions about that? So the assumptions really matter. The more independence you assume, the better bounds on the probability you get of a match. It's a little bit unrelated to this, but there was another mathematics dispute at the OJ trial. It turned out that OJ had been beating up Nicole on a fairly regular basis, and there were police records, because after he beat her up, she'd go in and complain to the police. And the prosecution wanted this evidence admitted at the trial. Because if the guy's a wife beater, that's makes you think that maybe he killed her. And the defense lawyers argued against admitting that evidence because it wasn't tied to the actual murder scene in any way. And they argued it would be prejudicial to the jury because, of course, if the jury hears that O.J. was beating her, they might be more likely to incline to convict him for murdering her. Now, they got the math counsel again to argue that the reason you shouldn't admit this is because the probability that you kill your wife that's K. Given that you batter your wife, that's B, is 1 in 2,000. I would have guessed it was higher, but that's what they did evidence that showed that. And so they said, look, there's only a 1 in 2,000 chance that this evidence of wife beating is relevant. And therefore, it should not be admitted because there's a pretty decent chance if the jury hears this, they're going to convict him. That's a pretty good argument, you know, and usually for that kind of thing, you exclude it. Yeah?
Where did that number come from?
They got some study and some experts to come in and say that only, you know, for every 2,000 wife beaters, only one of them actually kills his wife. You know. All right, now what do you suppose the prosecution argued back? They actually argued back very effectively, because that's a tough argument to get by. Yeah?
What's the probability that you kill your wife in like the first place? That could be 100 times larger than usual.
Well, that's a good point. So maybe the probability of killing your wife not knowing B probably is, I hope it's pretty small. All right? And probably that's very small, but I don't know. But in any case, this thing, you're going from, say it's 1 in a million to 1 in 2,000. 1 in 2,000 is still too small to be used as evidence that O.J. did it. Frequency, they didn't get into that because I guess he'd done it a bunch, but that's a good point. It could be there's multiple beatings is a higher. Maybe that's 1 in 200 then. In fact, that may be the case because I think there's probably statistics that say if you do it once, you do it multiple times. You know, so there's not much more to be gained there. There's a critical piece of information we've left out of our conditional probabilities here. In fact, the most glaring piece of all of evidence. What's missing here? What haven't we factored in? Yeah?
B.
Probability of B, that's the battering. Battering, I don't know what it is, probably a large number. You know, defense would argue it's large, I guess, but shouldn't matter that much. Well, there's that, but they had police, well, that's true, they didn't see him doing it, but let's say that they had good evidence that he did it, and the defense wasn't arguing that he didn't really beat her. All right, the key thing we're missing here is Nicole wound up dead. She was dead. All right, and there's another stat here that the prosecution argued. They argued that the probability that the husband did it so they argued this fact. Probability the husband kills his wife given that he batters her and she wound up dead, that somebody murdered her, is bigger than a half. So here M is somebody murdered the wife. All right, here's the husband beats her. Now the probability, conditional probability that he killed her is bigger than a half. And that's a whopper. Now it's very relevant. Right? The probability he killed her just given that he beat her is only 1 in 2,000. But if you add the fact, which is very relevant in this case, that the wife was murdered, this is now very compelling. Now, in fact, they should have really compared this to probability he kills her given that she's dead. And so that would determine now the relevance of the battering, the wife beating. That's what they should have done, but they didn't. They got this far, and they had that, and the judge said, I'm letting it in. Okay, so it came in at that point. But this would be the right comparison, I think, because you look at the probability that you killed her versus, given that she's dead, but now the additional information of the wife battering, how does that change the probability? And it probably changes it materially. Okay, so it's all a little gory, but it's interesting to see how mathematics played out, in this kind of an environment. Yeah?
Assume that he didn't kill his wife?
Yes, and they assume that, but when you decide whether or not to admit evidence, if it's prejudicial, you've got to have a really good grounds to get it in. Like, if the evidence is going to make the jury think he did it, then you really got to argue the evidence is relevant somehow, that it's material information. And that's what the fight was about. A 1 in 2,000 relevance isn't going to cut it. 1 in 2, that's probably pretty relevant. And that will be the grounds on which the judge makes his decision. But yeah, you assume he didn't do it. Okay. All right, back to independence. So the last example today is derived from a famous paradox and has several actually important applications in computer science. And this problem is known as the birthday problem or the birthday paradox. It's a paradox because it sort of has a surprising answer. Probably a lot of you have seen this before in some form or another. In the birthday problem, there are n birthdays. And typically, we're going to look at the case where n is 365, so the days of the year. And there's m people. And for example, I don't know, maybe there's 100 people here. And what we want to know is what is the probability that two or more people have the same birthday. For example, how many people think there's at least a 50% chance that a pair of you in the audience here have the same birthday? Yeah, good. That's good. How many people think there's a better than 90% chance? A few of you. All right, how many people think there's a better than a 99% chance there's a pair of matching birthdays? A couple left. All right, how many think it's better than a 99.9% chance? I got 1, 2. You guys are going to be stubborn. Oh, another one. All right, how many people think it's more than 99.999% chance? All right. Actually, it's 6 nines. It's incredible. It is a virtual certainty. So let's see. In fact, the chance that you're all different is about 1 in 3 million chance that you're all different. All right, and we're going to see why that's true here. But to do that, we're going to need to make 2 important assumptions. Any ideas about what assumptions we're going to need? Yeah?
Distributed?
Birthdays are uniformly distributed. Any other ideas? Yeah?
I stole mine.
Oh, you stole yours. Okay. What else are we going to need to assume? Yeah?
All birthdays are independent of each other.
Yeah, mutually independent. We're going to need that as well. Now, in actuality, neither is true in reality. It's well known that birthdays tend to follow seasonal patterns, and they're related to major events. Now, do you all remember the big blackout that hit the Northeast several years ago? You remember that? Well, it turns out, this is a true fact, there were a lot of babies born 9 months later. In fact, they had a name. They're called blackout babies if you were born in that period in the Northeast. And there's all these news stories about the life of the blackout babies. And the same thing happens after cold snaps in the winter. You get a blizzard or this kind of a thing. 9 months later, you get babies. In fact, I had a personal experience with this. My son was born on October 18th, 1996. And on the day he was born, we're going to the hospital, and it was a zoo. The maternity ward was totally full. We had to go at some other wing of the hospital. And, babies were popping out all over the place. And I asked, what is going on? Why don't you have enough room, for all the mothers here? And they said, oh, it's all the blizzard babies. And I go, what? And they go, well, remember the blizzard of 96? It's like, oh, yeah. Yeah, I remember. Yeah, it was 9 months prior, it's the big blizzard, and so it's all the blizzard babies coming. So they're not uniform. They're all different probabilities here, but we're going to assume they're equally likely. Now, independence is also not true in general. What's one way that birthdays might not be independent? What is it? Twins. All right, so if they're twins, they have the same birthday. Now, there's other ways. In fact, my only sibling, my brother, has the same birthday I do, but I'm 2 years older. So we weren't twins. Now you say, what are the odds of that? Well, 1 in 365, you'd think. And, well, you know, one day I'm in middle school, about the age you start thinking about these things, and you get the idea to count back 9 months from your birthday. Probably some of you have done that. And, you know, I did that, and, oh, that's my dad's birthday. Now, you know, it's like, oh, you know, maybe it's not 1 in 365, you know. It's like, you know, happy birthday, you know. It's like, I don't know. Anyway, I almost needed to go into therapy after that, you know. It's, so now you all got to count back 9 months from your birthday, right? It's like anybody's birthday on September 30th or October 1st, you know, 9 months back is New Year's Eve, you know. It's, this is dangerous. Anyway, so in reality, birthdays are not independent and they are not randomly distributed. But we're going to assume that because we're going to use this same analysis for computer science problems where things are hopefully more independent and random. Now we're going to do an experiment to see how many people it takes us to get a pair of matching birthdays. So I'm going to run through people in order in the rows here. Get your birthday, we're going to record them, and we're going to see how far we go until there's a match in that group. So we'll write up the months here. And we'll start with my birthday is October 28th. So let's go right across. What's yours?
April 1st.
April 1st. Okay. So that's, okay. We won't embarrass you here. Okay, who's next? What's your birthday?
I'm sorry,
September
September 2nd.
2nd. All right. Yours? June 1st. Okay, we'll come back. What is it? April 8th. All right. November 20th. June 12th. December 29th. What is it? June 14th. Ooh, we almost got one there. That was close. All right. What's yours? March 6th. May 2nd. November 17th. Close again. August 4th. July 25th. I don't think we'll get to 100 here, hopefully. Yeah. What's yours? What is it? October 30th. Got close. July 6th. All right. February 25th. All right. May what? 21st of May. Okay. May 30th. Okay. You guys aren't fooling me. What do you got? January 12th. All right. July 14th. Okay. April 30th. March 13th. All right, did I get October 7th? Ah, you guys. Okay. Did I get to you? September 15th. November 9th. Ah. All right. July 15th. Close. September 3rd. You guys are killing me here. February 6th. Okay. November 2nd. January 23rd. You guys are going to set a record for sure here. This isn't the way it's supposed to go. December 30th?
December 28th.
Oh, come on! We're going to have this probability of going this long here. Yeah? September 22nd. July 30th. 24th August. I may have to ask the same person to tell me twice here to get a match. We got over there now? April 6th.
October 16th.
October 16th. September 3rd. All right. Okay. Very good. All right, let's count and see how many we got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. That is a record. All right, so we took 42 people to get a match. Now, it turns out that for n equals 365, the magic number for m is 23. That by 23 people, we got a 50-50 chance. In fact, the probability of a match on 23 people is 0.506. So a little bit better than 50-50 chance at 23. Now, maybe we should figure out, it's too late for homework, figure out what the chances are of going this long without a match. That may be worth figuring that out. Now, you know, it may seem surprising at first that 23 people is enough to have a 50-50 chance, because the chance of any pair matching is 1 in 365 by our assumption. And that's small, but there's lots of pairs of people. And every pair of people have a chance to match. And that's why 23 turns out to be enough to get to 50-50. Now, we're going to do the analysis for general m and n to figure out the probability of a match if there's m people and n birthdays. There's lots of ways to do it. The easiest is to sort of, well, we'll draw the sample space. It'll be too big to draw the whole thing, but we can sort of model the sample space and then look at the sample points. Okay, so you've got the first person, and there's n birthdays here. So it could be anywhere from January 1st out to December 31st. And in general, this will be n. And then you have the second person. And they have n possibilities for their birthday. And you take the tree down m levels to the very last person here. All right? So each node has degree n, and there's m levels on this tree. So the sample space is the set of all n tuples, b1, b2 to bm. These are the birthdays, where every value of bi is between 1 and n. All right? So a sample point is all the birthdays of the n people. How many sample points are there here? Remember how to count these things? Number of leaves on an n-ary tree of depth m. Or you could think of it this way. I've got n choices for each bi, and there's m of them. So what's the number of sample points? N to the m. Okay, because n choices here, n choices here, n choices there. So you have n times n times n, m times. And what's the probability of each outcome? Each set of for a set of possible birthdays, what's its probability? What's the probability of B1, B2, Bn, Bm? So the probability of a sample point. What's the probability that the first person has birthday B1, the second has B2, and the mth has Bm? Remember that? Yeah? 1 over n to the m, because each edge is probability 1 over n. And you paths are length m, so you've got 1 over n to the mth power. Probability of the first birthday matching is 1 in n times 1 in n times 1 in n. All right, and this actually makes sense because I've got n to the m sample points, each with probability 1 over n to the m. So they all add up to 1, all right, which is good. What kind of sample space is this, where this happens, where all the probabilities are the same? Uniform. Makes it very easy to work with. All we got to do now is just count the number of sample points where there's a matching birthday. And then we multiply by that one probability, 1 over n to the m. OK, now it turns out that rather than counting the number of sample points where there's a matching birthday, it's easier to count the number of sample points where all the birthdays are different. And this is often the case when you're doing a counting problem. It's easier to count the opposite of what you're after. Just that can be the case, and it is the case here. So we're going to do that. OK, so let's count how many sample points are all different birthdays. So no pair of BIs is the same. Let's do that. How many choices are there for B1? 365 or n. Let's do it in terms of n because we're going to use this for general n. How many choices for B2? n minus 1. Given you already know the first one, you can't match it. And then n minus 2. All the way to the last one is n minus m plus 1. And this is a formula you should all remember. That's just n factorial over n minus m factorial. All right, you did this sort of stuff a couple of weeks ago with counting sets. And probability is really, a lot of it's about counting. So now we can compute the probability that all the birthdays are different. Is just adding up all the sample points, of which there's n factorial over n minus m factorial, and multiply by the probability of each one, which is 1 over n to the m. All right, so we've actually now answered the question. This is the probability that all the birthdays are different. The only problem is it's not so clear what the answer is to actually compute this or how fast it grows. So if I wanted to get a closed form for this without the factorials, what do I do? What do I use? Stirling's formula. OK? So let's remember that. It says that n factorial is asymptotically equal to square root 2 pi n times n over e to the n. And that is accurate to within 0.1% when n is at least 100. So not only is it asymptotically equal, it's right on track for a reasonable size n. Now, I won't drag you through all the calculations. I used to actually try. Plugging that formula in for here and here, and then going through all the calculations, but we won't do it in class. It's in the text. But I will tell you where that winds up. And it's not hard. You just got to do the calculation. So this means the probability that all birthdays are different turns out to be asymptotically equal to e to the n minus m plus a half times the natural log of n over n minus m minus m. And that's accurate to within 0.2% if n and n minus m are larger than 100. So in fact, it's almost equal. And now you can plug in n equals 365 and m equals 100. So if you do that, in fact, if somebody has a calculator, we should plug in, what did we have, 43? 42. We should plug in m equals 42 and see what the probability is. But if m is 100, the chance that we're all different, this equals 3.07 ... times 10 to the minus 7. And we should check for m equals 42. My guess is it's pretty small, but I don't know. We'll have to check that.
0.0859.
Great. So a 9% chance of going to having 42 people all miss is a 9% chance. So we were a little unlucky. That won't happen very often. But when you go from 42 to 100, it gets really small. 1 in 3 million or so. Now, if n is 365 and m is 23, the probability comes out to be about 0.49. So about 50-50, they're all different. OK. Now, for general m and n, we'd like to know when do you get to the 50-50 point. We'd like to derive an equation for m in terms of n where the probability of being all different is about a half. All right, so let's do that. OK, so as long as we assume, and this will turn out to be true, that m is little o of n to the 2/3, and remember little o means it grows slower than n to the 2/3, then we can simplify that expression in asymptotic notation. And when you do it, I won't drag you through on the board. It's also in the text. It turns out to be much simpler. It's just e to the minus m squared over 2n. So I take that thing up there, and I assume that m is growing less fast than the 2/3 power of n, and that whole upper expression reduces down to m squared over 2n. Everything else goes to 0 in the exponent. Doesn't matter. Now, if I set this to be a half, I can solve this to find out what m has to be to make that be a half. All right, so this will be true if and only if minus m squared over 2n is equal to the natural log of a half. And that's true. Take the minus sign, put it inside to make it log of 2, multiply by 2n. That's true if m squared equals 2n natural log of 2. And now I solve for m really easily. That's true if and only if m equals the square root of 2 natural log of 2n, which is about 1.177 square root of n. So for general n, you get a 50% probability of having a matching birthday when m is in this range. OK, pretty close to 1.2 square root of n. All right, now this square root n phenomenon, this thing here, that's what's known as the birthday principle. OK, it says that if you've got roughly square root of n randomly allocated items into n boxes or bins or birthdays, there's a decent chance 2 of the items will go into the same bin if they're randomly allocated. OK, in this case, the bins are the possible days of the year that we put each person into for their birthday. Any questions about that? Yeah.
They're defined up there. What does it mean to say m equals O of n?
Yeah. So here I looked at a special case where n was 365 and n was 100. But we can imagine them as arbitrary numbers that could be getting large. And so over here, when I say m is little o of n to the 2/3, I mean, for example, well, m equals square root of n would qualify. Square root of n is little o of n to the 2/3. Okay, so as long as m is not growing too fast, I can simplify that expression up there, which is what I did. And then we go back and we find, in fact, square root of n is the right answer, and that is little o of n to the 2/3. And I'd have to use a different argument if I assumed m was bigger, which I didn't do. I didn't drag you through that. But I would have to go check that case. Okay? So we can think of generally as m and n as being arbitrary variables and potentially growing. M could be a function of n. And in fact, when m is the square root function of n, then we got a 50% chance of a match. Okay. Now, this principle comes up, the birthday principle comes up all over the place in computer science. And it's worth remembering. For example, the generic form for this is when you have a hash function. Say I have a hash function, h, from a large set of items into a small set of items. For example, say I'm computing digital signatures. This is the space of all messages. This is the space of all 1,000-bit digital signatures. And h is the digital signature algorithm. Say I'm doing memory allocation. So all the things I might be sticking into a register, here's all the places it could go. Here's all the registers. Error checking. This is all the garbled messages in the world. This is the set of messages that make sense. All right, all handled by functions, random kind of functions often. Now, what you worry about when you're hashing is collisions. Let me define that. We say that x collides with y if the hash of x equals the hash of y, but x and y are different. For example, say you're looking at digital signatures. You would not want the signature for a $100 check to your mom to match your signature for a $100,000 check to Boris. Okay? Because that would be bad, because then Boris could come in and take that check to your mom for $100, convert it to a $100,000 check to him, and the signature is authentic if there's a collision in the signatures. All right, so very important when you're doing hash functions in many applications, you don't want collisions, right? Because the whole thing starts breaking. Memory allocation, you don't want to assign two things to the same place. Error correction, there's only one answer you want to get out at the end. Okay, now from the pigeonhole principle, you know that if this set's bigger than that set, there's going to be a collision. That's what the pigeonhole principle says. Two guys will get mapped to the same thing. However, often in practice, what we care about is a subset L prime of L that's pretty small, because the set of messages we really sign is pretty small compared to all 1,000-bit signatures that are possible. And what you'd like is that for this smaller set of messages you might want to sign, that they all get mapped 1-to-1. And the birthday principle says life is not so nice. So let me write that down, and then we'll be done. All right, so the birthday principle says that if S is at least 100, L prime is a subset of L that is at least the square root of S. So the cardinality of the things you want to hash is bigger than 1.2 square root the cardinality of S. And if the values of the function h on L prime are randomly chosen, uniform. And mutually independent then there's at least a 50% chance, so with probability at least a half, there's a collision. There exists an x and a y such that x does not equal y, and these are an L prime, but h of x equals h of y. All right, the proof is not hard. It's just we more or less did it. You just plug in the cardinality of L prime for m and the cardinality of s for n. And it's bad news because it means it doesn't take very many messages. Just square root the number of signatures to get a collision. You know, you'd hope you could get that you could have L prime be as big as s, and somehow they'd all go 1 to 1, that everybody in this room would have a different birthday. That is not how it works if things are random, which is the case you usually like to have. Now, this technique is used to crack cryptographic protocols, and it's called the birthday attack, based on the birthday principle. So what you do is you get a bunch of messages that are encrypted, and pretty soon you find 2 that get maybe encrypted the same way. And once you have that, now you can go back and crack the crypto system. For example, you break schemes like RSA with a birthday attack if the space is not big enough. And that's one reason why now RSA, the keys, have thousands of digits. Because otherwise you can use attacks like this and, you know, crack them more easily. Okay, any questions about that? Okay, very good. We're done for today.